Hi, I'm Elijah, and this is my project on pacman and deep Q networks. First, I'll introduce the topic, then I'll share my hypothesis, talk about my project, show results, and then dive into issues and next steps. So I'll start with some background on DQNs. Q-learning is a reinforcement learning algorithm that works by updating a Q table to estimate how good an action is at a given state environment. The problem is that our state action space is very large. Even just the screen input for Miss Pac-Man is 33,600 RGB pixels. There are also 8 actions, so learning this table would be really, really hard. Instead, we can replace this with 2 neural networks, in my case CNNs, and this is called a double deep Q network. We put 2 networks so that one can be a lagging target network for the policy network. Researchers have applied DQNs to a whole bunch of Atari 2600 games, and Pac-Man doesn't get much of a performance boost from DQNs as opposed to other games, still performing much worse than humans. My hypothesis explores this. I think power-up pellets confuse the network. It makes Pac-Man switch between 2 opposite behaviors, running away and chasing ghosts. This is hard to learn. To test this, I see if removing rewards related to eating ghosts helps performance. I also try seeing if reversing Pac-Man's movements while powered up helps. The last experiment I still need to perform is trying 2 separate DQNs, one for each scenario. This project demonstrates tactics to improve performance, especially within settings of low computational resources when neural networks might not have a chance to stably converge. Since my midterm report, I've learned about DQNs and fixed bugs in the original code. I wrote a script to determine invincibility frames of Miss Pac-Man after eating a power pellet, coded different behaviors triggered by certain score rewards, ran 10K frames on all of my hypotheses except one, and I generated plots for visualization. Here are the results. As you can see, removing rewards from eating ghosts and initializing in the reverse direction both helped boost the average logarithmic rewards across the last 20 games. You can see that the default algorithm ran more games than 10,000 steps, suggesting it also died more often. Also, purely qualitatively, the default curve seems much jumpier. I hope to quantify this variance as a next step. The default also had the highest range of loss per optimization step, again indicating unpredictable growth. The default also had the highest predicted Q values. And this is to be expected because removing ghost rewards should of course result in a lower predicted Q value because there are less rewards available. Here are the most important code alterations I made, grouped by topic. On the right-hand side, you can see the models, plots, and data generated for one of my experiments. And this is a demo of that experiment running. Here, the Q network doesn't know that Pac-Man gets rewarded for eating ghosts. The idea is that without this having to switch between chasing and running away, Pac-Man can focus on survival. Next, I'll talk about issues and next steps. I think that the issue of finding more quantitative metrics to compare these different learning curves can be solved by running the code more times for more robust comparisons, sort of taking the average or looking at the variance between these runs. I also would like to see if these improvements hold up in the long run past 1,000 episodes, or if the default CNNs catch up to these optimizations. I also plan to implement that final experiment that I haven't gotten to yet. For next steps, I hope to fix all these issues, and if I have more time, I'd like to implement dueling DQNs and try gradual steps between the networks. Another possible idea is to pre-process the ghost colors to be the same shade of gray to see if the algorithm is learning each ghost's personality or if that's not really affecting its performance. Thank you.